Welcome back to my series of videos. I want to talk with you about this function. I want to talk about this function with you. We talked in class about this limit being 1. I said that the limit as x approaches 0 of this function is equal to 1, and I didn't prove it to you. But I wanted to work with you right now to talk about the various pieces of the definition of the limit, the formal definition, to explain why this limit is 1 and how those different pieces of the definition of the limit fit together to be able to let us prove that functions have limits at certain places. So the first thing I'd like you to do is to just focus on this function. Just focus on this function. Focus your attention down here on x values near x equals 0. Focus your attention down there. And these values down here. And then look up into the top of the function right here. We're measuring heights right here. We're measuring heights of our function. That's what our limits are all about, is heights of functions. Note that I've got an empty circle there at the top. Why do I have an empty circle there at the top? Why do I have an empty circle there at the top? I have an empty circle up there at the top because I can't evaluate my function at 0. It's ill-defined. Sine of 0 is 0. X evaluated at 0 is 0. So the function is 0 over 0 at that point. At that point. Remember, 0 over 0 is a mask behind which hides any number or any not a number. So our mission is to peel away the mask, and the graph in this particular instance is going to be the thing that we're going to use to peel away the mask, to figure out what number hides there as x goes to 0. So we're going to look at the limit as x approaches 0 of sine x over x. The limit wants us to engage in a gap-finding process, in a sense. The limit is the value L, so that if I take function values near my value of concern, which I'm going to put down here, so this is where A lives. A lives down here on the x-axis. Right. So here's A. And I should be able to, what I want is for you to be able to go down to Davies and ask somebody for a small number, and you just take whatever small number they give you, regardless of how not small it happens to be. Small is also a matter of context. So I'll bet you get different answers if you ask like biologists, like macrobiologists versus like microbiologists. I'll bet you get different answers for what small numbers are. So I propose to you that the number L, which is 1 in this case, forgive my stray mark, is equal to the limit. I propose that that number is the limit. So go down to Davies, ask a random person for a small number. And they're going to give you a small number, and that defines a window about your proposed limit value. And then we need to go down here and find a window around A so that function values within the window down here map within those up here. So this thing right here, there's a distance between between L and the function value in the output, right? And they're calling this in the book, they call this the gap. Mind the gap. A symbolic way of writing the gap is as, so the gap is f of x minus L. It measures the distance between heights here and how far off from the limit you are. And we want this to be arbitrarily small. This distance here should be able to be set to some small distance by any random person you ask. They give you some small number, and we have to find a window down here. that maps through it through the function. So this thing we want to be arbitrarily small. Want it to be arbitrarily small, right? It's small, and the smallness of it is not up to us. We're not in control of how small it is. Somebody else is. So, we go down to daties, and we ask some person for their small value, and they're like, well, let your small value be 0.2. And we're like, challenge accepted. Okay, it's not up to me, but it really is the limit. 1 really is the limit of that function. So regardless of whatever value you give me, I'm going to be able to engage in the windowing process. So I'm going to investigate function values around this output value, like meow. And they're saying that we want to be within 0.2 in either direction of L. So L is at the center of a window, of a gap, and then I'm going down as far as 0.8. I'm going to go up as far as 1.2, because that's L plus small value and L minus small value. Now, I have owned a number of animals in my lifetime, and I know that calling it the cat or the dog gets burdensome after some while, and we should just have a name for it. So instead of saying the small value, I'm going to replace it with a symbol name, but it just means the small value that's not up to us. Just means the small value that's not up to us. And the classic name for this quantity is a Greek E. It's an epsilon. Okay. So, we've got a gap determined by L plus epsilon and L minus epsilon. Now what we want to do is be able to find a window about A so that function values map in here. So I'm going to take my things and draw a cross to define my window. Yep, they show up. And then I'm going to plop down there. And it should be symmetric. My drawing is imperfect, so it's not symmetric, but it should be perfect. So so as long as I'm in the window right here, oh, I could do that in the color that looks orange currently. This is actually a pink marker. So as long as I'm inside of this window here, which is centered about A, I end up inside of this vertical window, which is centered at L. So this distance here, the distance between A and the outer boundaries here, we call that value, the classic name for that value is delta. And it's not a capital delta, it's a lowercase Greek d. Right? So the distance, this is the distance away you get to be from A. So there are a bunch of different ways to find this. There are algebraic techniques, and I'm not going to cover algebraic techniques for finding these in this video. That's a different video that I haven't made yet. But another way that you could, so a way that you could do this is you could be all like, hey, what's up, TI-84? I'm going to Y equals button you, and I'm going to put in our friend sine of x over x, sine x divided by x. I'm going to go zoom 6 for standard. I'm going to plot it inside the standard window. It's not going to look quite like this because the axes are going to be different. So maybe now I'll adjust the window to be like y min. I'm going to put y min to be like, say, minus 0.5 and y max. I know. And y max to be, so I want that to be minus 0.5. And I want the y max to be, say, like 1.2. And I'm going to graph it. Oh, yeah, this looks, oh, this is, yeah. Spot on. Uh-huh. You should totally plot this function. This is great. This is just incredible. I really wish you could see this. Right? So if we plot this thing, just looking at this graph, I have no idea, just looking at the graph, that this hole is here. The calculator just completely skipped over it, which is one of the reasons why I, in some ways, distrust computer plots, because they just skip things like that. Okay, so I plotted my function, and you should totally do this. Like right now, you should like plot sine x over x on your calculator with a standard window, but then just trim the y direction for a little bit. And now I'm going to push trace. That's going to give me a little cursor. I got a little cursor, and it's attached to my thing. I'm going to push my left and right buttons. Got my left and right buttons over here, and that's going to move the cursor left and right, up and down, and it's going to trace out the curve. And what I'm going to do is I'm starting x equals 0, and it's not giving me a y value because it's not defined there. And I'm just going to like move to the right until I get down to 0.8 in the y value. There we go. Okay, so it's going at 1.0638. Its y is 0.8217. That's still within. If I go one more, it's 0.74. So how about we call this outer value right here? I could do better, but we're just going to call it. If I zoom in more, like we could find out what it is. So I'm going to call that value 1.0638. And then I'm going to go to the left. I'm going to go this way. And I'm going to find, where does this thing drop out of this window? Scrolling. Well, it's going to be, the thing is symmetric, as is their discretization. So it's going to be the same value with a minus sign. I'm verifying that on my screen right now. It says minus 1.0638. Yep. Sweet. And that's this value here. Okay. And both of those function values are bigger than 0.8. So they're within 0.2 of this value 1, the limiting value, the proposed limit. So as long as, check this out, so as long as a is within in this window, my function values are in here. So what I'm going to do is I'm going to calculate these two distances, which for most functions will be different from each other. So there's two distance here. There's like delta sub 1, and oh, that's an 8, but I meant it to be a delta. Whoop. Delta sub 2, right? There's the direction like left and the direction right. So or it could also be like delta minus and like delta plus if I wanted. So I'm going to take delta to be the smaller of those two things. So I'm going to choose delta to be the smaller of delta minus and delta plus. Those two numbers both happen to be 1.0638. How about we just call it 1 because that's even smaller, and that's fine. So let's make it something nicer. So let's make that be like 1. I don't know. I don't know whether to put the 1.0638 or not. I'm gonna do it. Okay. Now, if I don't know why I put those horizontal lines there. So if the absolute value between x and a, which is 0, so that's a distance down here. That's a distance your x is away from a. If x minus 0 is less than delta, then the absolute value of f of x minus L, which is 1, that's an absolute value sign, is less than epsilon. That is off screen. Fine, I'm zooming out. The curtain is shattered, you can see the magic behind the screen. Right, so as long as I'm within this window, if x minus a is less than delta, if we're in this window, then f of x minus 1, or f of x minus L, the difference in the function value at a and the target value L, up here, is less than epsilon. And this is exactly the definition of the limit, right? This is exactly the definition of the limit. We have some arbitrarily small value. It wasn't up to us. You, as the viewer, didn't choose 0.2, right? I chose that, and I got that by asking some person down in Davies, right? And then I'm like, oh, well, I can reverse engineer this problem. Fine. You want it to be so small? Then all I have to do is take A in here, and boom, we're inside of there, right? Boom, we're inside. So if x minus a is less than delta, then f of x minus L is less than epsilon. Therefore, big right arrow with 2 bars, I get to write my conclusion to this problem, that the limit as x approaches 0 of sine of x over x is equal to 1. Okay, I don't get to write that. I don't get to write that, and the reason that I don't get to do this yet is because I only did this for one particular value of 0.2. I didn't do it for a generic value. I did it for one specific value. What if somebody just made epsilon smaller and I failed to be able to do this process? But the point is that for this function, no matter what you choose for epsilon, no matter what somebody down at Davies chooses for epsilon, no matter how small you make this window, you're always going to be able to put a window right here so that function values are inside that top one. You can always see the function inside of that tiny little window that's defined up there. You can always squeeze the function values into the gap if you just make it small enough down here, if you just find a small enough delta. And that's what it means for the limit of sine of x over x as x approaches 0 to equal 1. It's been satisfied. I'm going to stop there and say thank you very much and have a nice day. Bye.